Hello everyone, and welcome back to another Physics Friday. I am very excited about this one in particular because this really is the intersection of two series, namely Physics Friday, but then also Squircles. And what we're going to be doing today in this video is finding the moment of inertia of a Squircle. And to be a bit more specific, say we have our little Squircle here, if I can actually draw a Squircle. We're going to be rotating it about this axis right here. So imagine like a squircular fidget spinner. So without further ado, let's get started. Our formula for finding moment of inertia is going to be the one you have, on like the AP, the one you see on the AP Physics cheat sheet, and the one you see most commonly online. Though I must say I do not love the way this is expressed because really this integral right here is can range from being a integral to 3 integrals, which is a bit annoying. Grievances aside, let's start by dealing with this dm term. So this dm term, well, what's m? M is just mass, and one way we can express mass, so mass is equal to volume times density, right? If we say that our Squircle has uniform density, we can say density is equal to mass over volume. Or, in other words, we can say density is equal to dm over dv. So dm is literally just dv times density. Or in this case, dA, because we have area, and that's where it's being distributed. So really, we have dm is equal to our density times dA. In this case, because we're going to be using Cartesian coordinates, this is going to be rho dy dx. So now that we've taken care of the differentials, let's take care of the actual integral bits now. So what our integral is actually going to be, if I kind of zoom in on this, is double integral over our Squircle. So I'll just write Squircle for now. Bring our density up front of r squared times dy dx. But let's kind of break down what each of these bits actually are. So starting with r squared, what is r squared? R squared is just the distance from the axis of rotation. And going back to our little handy dandy picture right here, our distance from the axis of rotation is literally just going to be the distance from the origin in the xy plane. And again, the reason for that is just because we're rotating about this axis right here. It's going into and also out of the screen right now. So because of that, our distance from the axis is literally just going to be distance from the origin. And we can find that pretty easily using Cartesian coordinates. Like say I just pick a random point there, call that x and call that y and call that r. We see that x squared plus y squared is just r squared. So what's actually in our little differential right here is x squared plus y squared dy dx. And because we're integrating over a Squircle, our bounds are going to be as follows. It's going to be from negative r to r. And then our bounds for this second integral right here, or really first, because that'll be the order in which we're evaluating it. It's going to be r to the n minus x to the n to the 1 over n. And then similarly, just the same thing, but positive up in the top bound. So r to the n minus x to the n, all to the 1 over n. And then we have a rho out front. But again, our rho is just our density, which is just our mass, so call that big M, the mass of our said Squircle, divided by our area of it. And for the sake of brevity, I'm not going to write out the full area for a Squircle because that'd be a lot to copy down. So I'm just going to call this a Squircle right there, and we'll sub it in at the end. What we're going to do is do this first integral with respect to y, right? So we have our m over this right here, and then our second integral from negative r to r out front, of course. And then I'll write our dx and parentheses that we can just focus on this part. And what's the integral of x squared with respect to y? Well, the answer there is just going to be x squared times y, because x relative to y is effectively constant. So we have x squared times y, but y is ranging from negative this all the way up to positive that. So what y is going to evaluate to is just going to be 2 times whatever that is. To actually kind of write out what we're doing, we have y evaluated from, some negative quantity to some positive quantity. And because of that, we're just going to get 2 times said quantity times x squared. So we're going to have x squared and then times r to the n minus x to the n all to the 1 over n. And then don't forget the 2 out front. And then next for the y squared, well, this one is a bit more arguably straightforward. We're just going to have a 1/3 times y to the third. But similarly, we're going to have the top bound minus the bottom bound, but because this is a to the third, because the y is cubed, the negative can be pulled all the way through and it's going to cancel. So what we actually end up having is 2 times our quantity to the third. So this right here is just a 2. 2 times r to the n minus x to the n all to the 3 over n because it's cubed. Then we have dx. So all I have to do now to find the moment of inertia of a squircle is evaluate this rather long integral. So we've got this down to 1 dimensions, and we've done a lot of integrals like this before. So the substitution that we're going to make is just going to be the usual one. Get it? Usual one. These puns. Okay. We have u equals x to the n over r to the n. And what our differentials are going to be, we have du is equal to n times x to the n minus 1 over r to the n. I'm almost sick of these the substitution because I've done it so much. Squircles, but I love it still. But what we have, subbing everything in, right? We can see that x is just equal to u to the 1 over n times r, right? So this right here, there should be dx right there, pardon me. What we can see here is that subbing in this x, we have n over r, but then times u to the 1 minus 1 over n, and then r to the n minus 1. There should be an r to the n right there. And from this, you can probably see that the r to the n's cancel, and that just, there should be dx right here, which just leaves us with n over r times u to the 1 minus 1 over n dx. And just, this is all equal to du. So solving for dx, what we actually find, I'll zoom in on this part, is that dx is equal to r over n times u to the 1 over n minus 1 times du. So what we have now is m over a, our area of our squircle, times our integral from negative r to r. I'll deal with the bounds in like 1 second. And then we have our r over n. I kind of like writing, I like how they wrote the dx twice, that's funny. I write the du at the end, I suppose, this time. Then we have our u to the 1 over n. I should distribute it, so open parentheses. U to the 1 over n minus 1. And then what is this r to the n minus x to the n term in terms of u? Well, if we factor out an r to the n out of this whole expression right here, what we find is that, that this right here, this expression right here, it's equal to r times 1 minus x to the n over r to the n to the 1 over n. And that's just by properties of exponents, really. So when we factor that out, we see that this right here, this whole quantity is just u. So with that in mind, we can just say that, well, what I just underlined up there is just r times, I'll stick the r, actually I won't stick the r up front yet. So we have r, and then times 1 minus u to the 1 over n. But then keep in mind we have this extra x squared term right here. And what is x? Well, we really already solved for it. It's just 1 over n, or u to the 1 over n, times r. And squaring that, we have an r squared times u to the 1 over n. That's our first integral, or our first integrand simplified in terms of u. That should be 2 to the 2 over n. And then, what's our second one going to be? Well, this is going to be slightly simpler, actually, believe it or not. We have our 2/3 still, but notice whenever we factor out an r from here, we're going to get an r to the third by virtue of there's a big 3 right there. So what we have is r to the third times 1 minus u to the 3 over n. I'll erase that. If I was writing in pen, I'd just write over it, but we have erasers in OneNote. That's always handy. To 3 over n, and then times, well, our whole du thing right there, or most of it at least, because we already factored half of it out. So we have u to the 1 over n minus 1, close parentheses. And now, don't forget the du. And now here's actually something quite interesting. We see that even in the midst of all this chaos, that we have a common power of r to actually pull out of our integral. You'll see that we have an r to the third here, and that we have 1, 2, 3 r's right there. But then we also have a big R right there as well, out front. So we can actually factor out an r to the 4 out of this whole integral. So we can write this as m times r to the 4 over the area of a squircle, and then times over n, of course, times our integral of u to, simplifying this right here, so we have a u to the 1 over n, and then times u to the 2 over n, so this is going to be 3 over n, minus 1, times 1 minus u to the 1 over n, plus 2/3, or sorry, there should be a 2 out front. I do apologize. Plus 2/3 times r to, no r, we factored that out, times 1 minus, or actually to keep it in the same form, I'll put the u to the 1 over n minus 1 out front, then 1 minus u to the 3 over n du. And from this right here, our bounds are from negative r to r. And from this right here, you may be wondering a couple of things. How... I do apologize. These should be from negative 1 to 1. Negative 1 to 1, negative 1 to 1. I do apologize. Should have changed the bounds earlier. But at any rate, you'll see here that we have our bounds are from negative 1 to 1, which can be thought of as a little bit of an issue. But one of the sort of caveats with dealing with squircles is that there's almost an implied... Let me show you. So whenever we're doing the squircles, you'll see here that it's really symmetrical, right? Like this right bit is the same as the left bit, and the top bit is the same as the bottom bit. And whenever you type this into, say, Desmos, the equation that you're actually going to use to get the full squircle is not x to the n plus y to the n equals r to the n. It's actually the absolute value of x to the n plus the absolute value of y to the n equals r to the n. So really, I kind of dropped the absolute value signs just for the sake of brevity and to kind of avoid confusion. But the whole point of that there is that we can make these bounds, we can adjust these bounds as such because there is symmetry. So what we can do is kind of erase the bottom bound, replace it with 0, because again it's from negative 1 to 1, and just stick a 2 up front. And while we're at it, we might as well factor out another 2, right? And make this a 4. So that right there is our integral. And now we can just use our good old friend, the beta function. And what that's going to give us here, it's just going to be beta of 3 over n, comma 1 over n plus 1, plus 1/3 times beta of 1 over n, and then 3 over n plus 1. And there's interesting sort of symmetry going on here, so let's really investigate what that is all about. Expanding all of this in terms of the gamma function, we find that we have gamma of 3 over n, and then gamma of 1 over n plus 1, over, actually I'll do a small fraction bar to start, over gamma of 4 over n plus 1. And then for this next bit right here, we have 1/3 times gamma of 1 over n, and then gamma of 3 over n plus 1, and then divided by, that looks like a 2, we'll make that look more like an n, and then gamma of 4 over n plus 1. And here's the really interesting part. One way we can expand this term right here is by noting that gamma, so let me write this to the side, that this is this term right here. So we can say that gamma of 3 over n plus 1 is equal to gamma of 3 over n times 3 over n. That's just by properties of the gamma function. And whenever we invoke that, I say invoke, so fancy, whenever we apply that, sub it in, throw it in, plug and chug, we have this right here, and then times a 3 over n out front, but notice that we have a 3 in the denominator, so those are going to cancel, leaving us with just 1 over n, over gamma of 4 over n plus 1. But we have a 1 over n being multiplied by gamma of 1 over n, so we can just simplify that by properties of the beta function again. So this right here can just be gamma of 1 over n plus 1. And what we're left with is just the same thing as this right here. So what there really is what this sum is in total is just the following. It's going to be 2 times this. So we have 2 times gamma of 1 plus 1 over n plus 1, and then times gamma of 3 over n over gamma of 4 over n plus 1. And now that we've evaluated the integral parts, let's see what we have out front to deal with. What we have is a 4mr squared over a area of the squircle times n. So let's let's bring all of that down, shall we? We have, all right, it's another color actually. So we have a 4 times r to the 4 times our mass divided by the area of our squircle divided by n. So let's deal with this, shall we? And this is about the time where we do two things. First, it's going to be converting all of this to factorials, because I do, in my notes, have this in terms of factorials as well. So this right here in terms of factorials is just going to be 2 and then times 4 over n factorial, arguably nicer looking. And we have 3 over n minus 1 factorial, and then times 1 over n factorial. And our area for a squircle is just 4r squared times 1 over n factorial squared divided by 2 over n factorial. You should check out the original video. Or actually don't, because that was an old one. So really check out like the latest Squircle video before this. It was really fun to make. But anyway, with that shameless plug in mind, what we can do, because we're dividing by this, is flip everything and start canceling some things out. So first thing you might actually see is that these the 4 and the r squareds do cancel. So what this leaves us with is this right here, r squared times our mass, then divided by n. That's not going to change. But then we have our 2 up front still, and our fraction with all our factorials is going to look like this. So 3 over n minus 1 factorial times 1 over n factorial times 4 over n factorial, and then times 2 over n factorial divided by 1 over n factorial squared. And you'll see that a lot of things actually start to cancel quite nicely. This right here cancels with this exponent right here. And you'll see that we have this almost a little pesky n right here. But one thing we can do to kind of get rid of that is multiply everything by top and bottom by 3. So we can say, 3 over, I won't put the 3 out there, but we're just going to say 3 times this and 3n. That way, whenever we have 1 over 3n times 3 over n minus 1 factorial, we can just say that is 3 over n factorial. And what this gives us is the following. 2/3 r squared. Nice so far, right? And then we have 3 over n factorial times 2 over n factorial over 4 over n factorial, and then 1 over n factorial. And that right there is the formula, or really the moment of inertia, about like a central axis of a squircle. And you might be a little bit hesitant of this at first, which is, I'm gonna be dead honest, perfectly legitimate. Like, how on earth are you supposed to check this, or even make sense of it, right? Beyond just actually doing the integration yourself. And heuristically, you can kind of check this actually. Our math should be right there. Whoopsies. M is up front. Okay. And heuristically, I say heuristically, let's just plug in, say, n equals 2 to get a feel, or make sure this actually does work, because that would be good to check. So say we decide to plug in 2 to this equation. So let n equal 2, and our result there is going to be a solid circle rotated about, its like central axis. So we know that the result there should just be 1/2 mr squared. And let's just see if that is right. Whenever we plug in 2 right here, we see that we have 2/3 mr squared, and then times 3 over 2 factorial. But what's 3/2 factorial? Well, without getting into it too much, it is 3 over 4 times the square root of pi. And then what is 2 over 2 factorial? That's just 1. Yay, it's just 1. Okay, so then we have, in the denominator, 4 over 2 factorial, but 4 over 2 is just 2, so we're just going to stick a 2 there. And then we have a 1/2 factorial, but a 1/2 factorial is just going to be the square root of pi over 2. So what happens when we simplify all of this, right? Well, we see that the 2's cancel here, and that the 3's cancel here, and that the pi's cancel here. So a lot of cancellation. So you'll see that this 2 in the denominator is going to go up. So we have a 2 over 4, which is just 1/2, so 1/2 m times r squared. And that right there is indeed what we were looking for with the original formula. So to prevent this video from going on any longer than it needs to, thank you so much for watching. This is quite fun to make, and I will see you all in the next video, and also the next Physics Friday. Have a good one, y'all.